Welcome to the fascinating world of the periodic table, one of the most important concepts in chemistry. The periodic table is not just a chart, it's a powerful tool that organizes all known chemical elements in a way that reveals patterns and relationships. Whether you're a student, a researcher, or simply curious about how matter is structured, understanding the periodic table is essential. It helps us see that elements are not random, but belong to families with similar properties. In this video, we'll explore how elements are classified, why periodicity matters, and how these trends help us make sense of the chemical world. Imagine trying to study over 100 elements and their countless compounds individually. It would be overwhelming. Early scientists faced this challenge as more elements were discovered. To make sense of this growing list, they searched for a systematic way to organize their knowledge. Classification of elements not only made it easier to study their properties, but also allowed scientists to predict the existence and behavior of elements yet to be discovered. This systematic approach led to the development of the periodic table, which rationalizes chemical facts and guides further research. Journey to the modern periodic table began with early attempts to group elements by their properties. Johann Dobryner noticed that certain groups of three elements, called triads, had similar properties and that the middle element's atomic weight was about halfway between the other two. Although this law of triads worked for only a few elements, it was a crucial first step. Later, Aeb de Chancourtois arranged elements by increasing atomic weights in a cylindrical table, highlighting periodic recurrence of properties. These early efforts set the stage for more refined classifications. In 1865, John Newlands proposed the law of octaves, arranging elements in order of increasing atomic weights. He observed that every eighth element had properties similar to the first, much like musical octaves. While this pattern held true only up to calcium, Newlands' work was a significant step toward recognizing periodicity in element properties. His idea was initially met with skepticism, but it later gained recognition and contributed to the evolving understanding of elemental classification. Real breakthrough came with Dmitry Mendeleev, who arranged elements in increasing order of atomic weights and grouped those with similar properties together. Mendeleev's periodic law stated that the properties of elements are a periodic function of their atomic weights. He even left gaps for undiscovered elements, predicting their properties with remarkable accuracy. This boldness and success made Mendeleev's periodic table famous and laid the foundation for the modern table. Mendeleev's genius was evident in his predictions of elements like gallium and germanium, which were discovered later and matched his forecasts closely. By leaving gaps and trusting in periodic trends, he demonstrated the power of classification. His table not only organized known elements but also guided future discoveries, proving the value of a systematic approach to chemistry. The advances in atomic theory, the basis for classification shifted from atomic mass to atomic number. Henry Moseley's work in 1913 showed that atomic number, not mass, is the fundamental property of an element. The modern periodic law states that the properties of elements are periodic functions of their atomic numbers. This change brought clarity and resolved inconsistencies in earlier tables, leading to the periodic table we use today. Modern periodic table is arranged in 7 horizontal rows called periods and 18 vertical columns called groups. Elements in the same group have similar outer electronic configurations and thus similar properties. The table is divided into S, P, D, and F blocks based on the type of atomic orbitals being filled. This organization helps chemists quickly identify relationships and predict behaviors of elements. Naming new elements, especially those with atomic numbers above 100, can be contentious. The International Union of Pure and Applied Chemistry (IUPAC) provides systematic rules for naming these elements based on their atomic numbers until official names are agreed upon. This ensures consistency and avoids confusion, especially as new, unstable elements are synthesized in laboratories around the world. Arrangement of elements in periods reflects the filling of electron shells. Each period corresponds to the highest principal quantum number of the elements in that row. For example, the first period has 2 elements, filling the 1's orbital, while the second period fills the 2's and 2p orbitals, containing 8 elements. This pattern continues, with each new period introducing a new energy level and more elements. Elements in the same group share similar valence shell electronic configurations, leading to similar chemical properties. For example, all group 1 elements have an NS1 configuration, making them highly reactive metals. This group-wise similarity is a key reason why the periodic table is such a powerful tool for predicting element behavior and reactivity. S-block includes group 1 alkali metals and group 2 alkaline earth metals, characterized by NS1 and NS2 outer electronic configurations. These elements are highly reactive metals with low ionization enthalpies. They readily lose electrons to form positive ions and are never found in pure form in nature due to their reactivity. Their compounds, except those of lithium and beryllium, are predominantly ionic. P-block consists of groups 13 to 18, and together with the S-block forms the main group elements. Their outermost electronic configurations range from Nstin P1 to Nstin P6. The P-block includes a wide variety of elements from metals to nonmetals and metalloids. Notably, the noble gases at the end of each period have a stable, closed-shell configuration, making them largely unreactive. D-block or transition elements occupy the center of the periodic table, groups 3 to 12. These elements are characterized by the filling of inner d orbitals and have general configurations of N1D1-10 and S0-2. Transition metals are known for forming colored ions, variable oxidation states, and often act as catalysts. They bridge the chemically active S-block metals and the less active P-block element. F-block elements, also known as intertransition elements, are found at the bottom of the periodic table. They include the lanthanoids and actinoids, characterized by the filling of F orbitals. These elements are all metals and often have similar properties within each series. Many actinoids are radioactive, and some have only been produced in trace amounts in laboratories. Periodic table also divides elements into metals, nonmetals, and metalloids. Metals, which make up over 78% of known elements, are typically solid, shiny, and good conductors. Nonmetals, found on the top right, are usually gases or brittle solids with low conductivity. Metalloids, such as silicon and germanium, have properties intermediate between metals and nonmetals, and are found along the zigzag lines separating the two. One of the most noticeable periodic trends is the change in atomic radius. As you move across a period from left to right, atomic radius decreases due to increasing nuclear charge pulling electrons closer. Down a group, atomic radius increases because additional electron shells are added, placing outer electrons further from the nucleus. These trends help explain many chemical behaviors. When atoms gain or lose electrons to form ions, their sizes change. Cations' positive ions are smaller than their parent atoms, while anions' negative ions are larger. Isoelectronic species ions or atoms with the same number of electrons can be compared by their nuclear charge. The higher the charge, the smaller the radius. These concepts are crucial for understanding ionic compounds and their properties. Ionization enthalpy is the energy required to remove an electron from an atom in its gaseous state. The first ionization enthalpy increases across a period and decreases down a group. This trend is influenced by atomic radius and effective nuclear charge. Elements with low ionization enthalpy, like alkali metals, lose electrons easily, making them highly reactive. Electron gain enthalpy measures the energy change when an atom gains an electron. Elements like halogens have highly negative electron gain enthalpies, as they readily accept electrons to achieve stable configurations. In contrast, noble gases have positive values, as adding an electron disrupts their stable arrangement. These trends help explain why some elements form anions more easily than others. Electronegativity is a measure of an atom's ability to attract shared electrons in a chemical bond. It increases across a period and decreases down a group. Fluorine is the most electronegative element, while alkali metals are among the least. Electronegativity trends are closely related to atomic radius and help predict the type of bonding between elements. Valence refers to the combining capacity of an element, often linked to the number of electrons in its outer shell. Oxidation state is a related concept, indicating the charge an atom would have if all bonds were ionic. These properties follow periodic trends and are key to understanding how elements form compounds. For example, group 1 elements typically have a valence of 1, while group 17 elements have a valence of 1 or 7. Elements in the second period, such as lithium and beryllium, often show properties different from others in their group. This is due to their small size, high charge-to-radius ratio, and limited number of valence orbitals. These elements can form multiple bonds and have unique chemical behaviors, a phenomenon known as the diagonal relationship. Chemical reactivity varies across the periodic table. Elements on the far left, like alkali metals, are highly reactive due to their low ionization enthalpy. They lose electrons easily. On the far right, halogens are also highly reactive, but because they gain electrons readily. Elements in the center, such as transition metals, are generally less reactive. This pattern is a direct result of periodic trends in atomic structure. Nature of oxides formed by elements also follows periodic trends. Elements on the left form basic oxides like sodium oxide, which react with water to form strong bases. Elements on the right form acidic oxides such as chlorine heptoxide, which produce strong acids in water. Elements in the center can form amphoteric or neutral oxides, showing both acidic and basic behavior. Transition metals, D block, and intertransition metals, F block, show unique trends. Their atomic radii change less across periods compared to main group elements, and their ionization enthalpies are intermediate. These elements often display variable oxidation states and form colored compounds, making them important in industrial and biological processes. Summarize: the periodic table organizes elements by increasing atomic number, revealing patterns in atomic radius, ionization enthalpy, electron gain enthalpy, electronegativity, and valence. These trends explain why elements behave the way they do, from their reactivity to the types of compounds they form. Understanding these patterns is key to mastering chemistry. Let's apply what we've learned. For example, where would you locate an element with atomic number 114? Using the periodic table, you'd find it in the 7th period and group 14. Such exercises help reinforce your understanding of how the table is structured and how to use it to predict properties. Isoelectronic species are atoms or ions with the same number of electrons. For example, O2, F Na+, and Mg2+ all have 10 electrons, however their sizes differ due to varying nuclear charges. The more positive the charge, the smaller the radius. Understanding isoelectronic species helps explain trends in ionic compounds and their properties. Cations are always smaller than their parent atoms because they lose electrons, reducing electron-electron repulsion. Anions, on the other hand, are larger due to the addition of electrons, which increases repulsion and expands the electron cloud. This fundamental difference is crucial in understanding ionic bonding and the structure of compounds. Each successive ionization enthalpy is higher than the previous one. Removing a second or third electron requires more energy, especially after the removal of all valence electrons. This is because electrons are being removed from a more positively charged ion, making the process increasingly difficult. This trend explains why elements form ions with specific charges. Electron gain enthalpy generally becomes more negative across a period. There are exceptions. For instance, oxygen and fluorine have less negative values than expected due to increased electron-electron repulsion in their small n equals 2 orbitals. In larger atoms like sulfur and chlorine, the added electron experiences less repulsion, making electron gain enthalpy more negative. Electronegativity differences between atoms determine the type of bond formed. Large differences lead to ionic bonds, while small differences result in covalent bonds. This concept is essential for predicting molecular structure and reactivity, and it's directly tied to periodic trends in electronegativity. Transition elements are known for exhibiting variable valence states. This is due to the similar energies of their ns and n1d electrons, allowing them to lose different numbers of electrons. As a result, they can form a variety of compounds with different oxidation states, contributing to their rich chemistry. Diagonal relationship refers to similarities between certain elements diagonally adjacent in the periodic table, such as lithium and magnesium. These similarities arise from comparable charge-to-radius ratios and electronegativities, leading to similar chemical behaviors despite being in different groups. Oxides formed by elements show a clear trend. Those on the left of the table are basic, those on the right are acidic, and those in the center are amphoteric or neutral. This reflects the underlying periodic trends in metallic and nonmetallic character and helps predict the behavior of compounds in reactions. Metals and nonmetals differ in many ways. Metals are typically shiny, malleable, ductile, and good conductors, while nonmetals are often dull, brittle, and poor conductors. These differences are rooted in their positions on the periodic table and their electronic structures, influencing their chemical and physical properties. The periodic table is more than a list, it's a predictive tool. By understanding trends, chemists can anticipate the properties and behaviors of unknown or newly discovered elements. This predictive power has driven discoveries and innovations in chemistry for over a century, making the table an indispensable resource. Let's quickly review the key periodic trends. Atomic radius decreases across a period and increases down a group. Ionization enthalpy increases across a period and decreases down a group. Electronegativity follows a similar pattern. Electron gain enthalpy becomes more negative across a period and less negative down a group. These trends are central to understanding chemical reactivity and bonding. Applying periodic trends allows us to predict the outcomes of chemical reactions, the stability of compounds, and the properties of new materials. For example, knowing that alkali metals are highly reactive helps explain why they are stored under oil, while the inertness of noble gases makes them useful in lighting and welding applications. The periodic table continues to inspire research and discovery. Scientists use it to guide the synthesis of new elements, design novel materials, and explore the boundaries of chemical knowledge. Its logical structure and predictive power make it a cornerstone of scientific progress. In summary, the periodic table is a dynamic, evolving tool that organizes elements by atomic number and reveals deep connections between their properties. Understanding periodic trends is essential for mastering chemistry, predicting reactions, and appreciating the beauty of the natural world at its most fundamental level. To reinforce your understanding, try answering some practice questions. What is the basic theme of organization in the periodic table? How do atomic radius and ionization enthalpy vary across periods and groups? These exercises will help solidify your grasp of periodic trends and their significance. The periodic table is just the beginning. As you continue your studies, you'll discover more about the unique behaviors of different groups, the role of electrons in bonding, and the fascinating exceptions that make chemistry so intriguing. Keep exploring and let the periodic table be your guide. Thank you for joining this journey through the classification of elements and periodicity and properties. The periodic table is more than a chart, it's a map of the building blocks of matter, revealing the logic and beauty of the chemical world. By mastering its trends and classifications, you unlock the secrets of chemistry and open the door to endless discovery.